Hello everyone, let's study about the velocity and acceleration in a simple harmonic motion. To understand this, let's recall the expression for displacement of a simple harmonic motion, which is given as y is equal to a into sine omega t plus phi. There are many forms of it. You can also write y is equal to a cos of omega t plus phi, or we can write in terms of x also. So any one form is sufficient. We'll take this form and take it from there. This is expression for displacement of a simple harmonic motion, where y is called as displacement, a is called acceleration, and this term in the bracket, which is omega t plus phi, that is called as phase, and this phi here is called as initial phase or epoch. This is what is the expression for displacement of a simple harmonic motion. Now we need to find its velocity. Let's simplify this further and write this as y is equal to a into sine omega t. We put phi is equal to 0. Now velocity is defined as the rate of change of displacement at any point of time. So write it, then the velocity of the particle is given as a rate of change of displacement that is equal to, again here think of y as just displacement. Don't assume that the particle moves along y direction, because here x or y indicates displacement, not necessarily along the x or y direction, just some displacement. So here it is equal to d by dt of a into sine of omega t. It is equal to, from here a comes out because a is a constant, a comes out, and what remains is it is d by dt of sine of omega t, and differentiating this, then what we get here would be a into omega comes out, it is differentiating, sine of omega t becomes omega into cos omega t. This is what is velocity at any point. Now here itself we can express the velocity in terms of the displacement itself. To understand this, let's recall what is y. We wrote that y is equal to a into sine omega t. We need to express this velocity in terms of displacement. Now from here we can say sine omega t is equal to y by a, or cos omega t is under root of 1 minus sine square omega t, that is using the form sine square x plus cos square x is equal to 1. Using this is what we get from here, that is equal to under root of 1 minus sine square would be y by a the whole square. Putting it back in velocity, then we get velocity as v is equal to a omega into under root of 1 minus y square by a square. If you take out LCM in the term inside, it becomes a into omega into under root of a square minus y square by a square. If a square comes out, it is under root, it becomes just a only. So it will be a omega under root of a square minus y square by a. From this, a gets cancelled, therefore velocity at any point is also equal to omega into under root of a square minus y square. So this is in terms of its amplitude and displacement. To understand this, let's consider a particle moving along a straight line, moving like this. As I told you, in this case y means just displacement from the mean position. So let the points a and b be the extreme ends of simple harmonic motion, and O is the reference point or the mean position. or the particle is somewhere here, then the displacement from O to this point, or point P, this is called as y. So y is the displacement from the mean position or equilibrium position. We learned in the previous lecture that when the particle starts from point O and goes towards point B, its speed or velocity will decrease. That's because when the particle is going towards B like this, the force is towards the mean position. The force is like this. So because the force and velocity are in opposite direction, velocity will decrease. At the point P, the particle stop and return and go back. So when the particle goes away from point O, velocity should decrease. Similarly, when the particle starts from point B and goes towards point O, velocity will increase because of this force. But since velocity and force are in the same direction, velocity will increase, because of which the particle at the point O will have the greatest speed because of the force, and the particle will not stop at the point O. Rather, the particle will cross point O because of its high speed or high velocity. Once the particle crosses point O, the force is again towards the mean position. Velocity will decrease. That is also seen from this expression. Now here we'll find where is velocity maximum and where is velocity minimum. So we'll take first case for velocity maximum. In this case, mathematically, if you look at the expression from here, for a given motion, omega remains constant and a remains constant, because a here is not this, right? Read as a point here. Let's call it some other point because a is already used here. We'll call as point P or point R and point Q. So distance between O to extreme position, which is Q or R, that is called as amplitude A. So for given motion, A remains fixed. Therefore, it depends only on y. If you want B to be maximum, this term should be maximum. But here A remains fixed and it is A square minus y square. So if this y is minimum, then this will be maximum. So it happens only if y is equal to 0. That's called as V maximum, and V maximum is equal to omega into, it will be under root of a square. Under root of a square is same as a only. Therefore, V maximum is equal to omega into a. So this is what is the maximum velocity. Similarly, you want to find minimum velocity. So for minimum velocity, this term should be as less as possible. We can't change omega, we can't change a. So by making y to be more, this term could be less. That happens if y is decreasing, and the maximum value of y would be a itself. That is, when the particle goes to extreme position, then y becomes a. So if y is equal to a, then v minimum is equal to 0. It is found out that whatever we studied physically, the same thing is obtained here mathematically also. So the velocity would be maximum at the mean position because of the restoring force, and velocity would be minimum at the extreme end. This is the expression for velocity in case of a simple harmonic motion. Acceleration is defined as the rate of change of velocity at any instant of time. Now, just to recall, velocity was given as a into omega into cos omega t. In terms of displacement, velocity was given as omega into under root of a square minus y square. Let's find out what is acceleration at any instant of time. So here we wrote omega v is equal to a into omega into cos omega t. Now here we differentiate v, then we get acceleration is equal to d by dt of a into omega into cos omega t. Again, from here a and omega are constants that come out of the differentiation symbol, and what remains would be a into omega d by dt of cos of omega t. Differentiating cos omega t with respect to time would give us minus omega into sin omega t. There's already a omega which is there, and therefore this will give us minus a into omega square into sin omega t. But recall that the displacement is given as a into sin omega t. So this term here is called as displacement y. Therefore, what we get here is acceleration is equal to minus of omega square into y. So here it is very obvious that the acceleration depends on displacement directly. The more the particle is away from the mean position, the more would be the acceleration or the displacement. Again here let's find what is the minimum and maximum acceleration. So for minimum acceleration as seen here, a would be minimum if y is equal to 0. So in this case it happens if y is equal to 0. Therefore a minimum would be 0. Similarly, for maximum acceleration, what we want is we want y to be maximum. The maximum value of y would be capital A. So when y is equal to capital A, mathematically it's a possibility. So when y is equal to capital A, which is the amplitude, then A becomes maximum, is equal to minus omega square into A. This is what is A maximum. As seen here, we find a minus sign, means that the acceleration is always negative of the displacement. That is because if we look at this case where particle is say moving, let's draw a diagram for it. Redraw this. Think of a case where the particle moves between two extreme positions. Let's call it as R, and this is point Q, and somewhere here is the mean position O. When the particle is going like this, y is increasing. When y is increasing, the acceleration or the force would be towards the mean position. So here y is increasing, but force is against the displacement. That's the reason that the sign is negative. So mathematically, a minus sign means that A is negative to displacement. This is what we define as a simple harmonic motion. We define S.H.M as saying that it is a motion where the acceleration is directly proportional to the displacement and it is opposite displacement. Even here also, if you look at a point from here, the particle moves like this also. Even in this case also, the velocity is like this, the force is towards the center. So even here, acceleration is towards the mean position. So wherever the particle is moving, even here also it moves in this line also, it is moving in the negative direction. So even here A would be negative. So what we got now was A is equal to minus omega square into y, and then omega is a constant, so you can say from here that A is proportional to minus of y. So this is actually the definition of a simple harmonic motion. To recall it, we say that in case of a simple harmonic motion, acceleration is always directly proportional to the displacement and it is negative of the displacement. Now to make sense out of the mathematical form, we got that A minimum is equal to 0. This happens at the mean position. That is because at this point the net force acting will be 0. so it will be 0, and A maximum is equal to minus of omega square into A. This is maximum value. So the more the particle is away from the mean position, the more will be the force acting it. Keep in mind that this is a case where A depends on Y, where A is not a constant, unlike violent in some other cases. So here A is a function of displacement also. Let's find out the phase relationship between displacement, velocity, and acceleration in case of a simple harmonic motion. To understand this, let's recall the equations for displacement, velocity, and acceleration. Y is equal to A into sin omega t was the equation for displacement. Velocity is equal to A into omega into cos omega t. And acceleration is equal to minus A omega square into sin omega t. If we look at expressions for displacement and velocity, displacement is a sine form and velocity is cosine form. So the phase difference between velocity and displacement would be pi by 2, because sine and cosine curves are out of phase by pi by 2. Similarly, velocity is a cosine curve and acceleration is a sine curve. So phase difference between velocity and acceleration is again pi by 2. That would mean that the phase difference between displacement and acceleration would be pi, because it is sine and sine curve only, but it's a minus sine, it's an inverted sine curve. So the phase difference would be pi between y and then a. Let's plot this graphically also. Now here there are 3 graphs plotted at some time interval. The first graph is a graph of displacement, which is y versus time. Second graph is a graph of velocity versus time, and third graph is a graph of acceleration versus time. Here we have taken 4 time intervals. So leaving the origin or the reference point, we are taken at interval of t by 4, t by 2, 3t by 4, t. We are finding how will the particles position, velocity, and acceleration be at these 4 time intervals. Understand this? Let's recall that y is equal to a sine of omega into t, but omega is equal to t by 2 pi. Therefore, it is a into sine of, or rather it is 2 pi by t, that's omega, is 2 pi by t. It becomes 2 pi by capital T, where capital T is its time period into small t. Similarly, velocity was a omega into cos of 2 pi capital T into small t, and a was equal to minus a omega square into sine of 2 pi capital T small t. This is what would be the curve for displacement, velocity, and acceleration. This is what graph we get. You can also verify mathematically by putting the time intervals as 0. Time is equal to say 1/4 the time period. Time is equal to say half of time period, 3/4 of time period, and then time is equal to time period itself. To understand this with the help of the motion also, let's assume that the extreme points are points R and then point 2. At the center was the mean position O, and we took a random point, say P. Now, the particle is starting from point O and going towards Q. We are assuming that the motion is like this. Let's assume this as plus direction and this as minus direction. So, the particle is going from point O to point Q. In this case, y is increasing. So, shown by this graph here, y is increasing. So, y as a function of time would increase. And the particle goes to extreme position. So, this corresponds to the position Q. So y has become maximum, which has become a in this case. When the particle is going back from point Q towards point O, it will gain speed, so displacement will decrease. So when the particle comes to point O, it will have zero displacement. So this corresponds to point O. Similarly, when the particle goes from O to R, it will have a negative displacement, which is shown by this graph, but it is still increasing because the more the particle goes away from O towards R, displacement will increase. It is increasing here, and it will have maximum value, which should be again A, but then it will be minus A because it is in the opposite direction. So this corresponds to point R, and finally when the particle goes from point R towards O, displacement will decrease. This corresponds to point R. This is what is the curve for displacement. If we look at the curve for velocity, if we look at physically, at the starting point, velocity is maximum. That is shown by this value omega into A, because in this case the maximum amplitude is A into omega. This is called as A into omega. This is what we get here. When the particle goes from point O towards point Q, we know that velocity will decrease. So velocity will decrease as given by this curve. At the extreme point Q, velocity would be 0. So this corresponds to point Q. When the particle turns back and goes towards O, it is moving in the negative direction. So velocity will be negative, but it is still increasing. The value of the speed is increasing. When the particle goes towards point O, the speed value will increase, but it is in the negative direction. So it is shown by negative half of the curve. When the particle goes to point O, speed is maximum. So this corresponds to point O. When the particle goes away from point O, it is still negative only because particle is towards the negative direction. It is going like this only. Here direction is very, very important, not the position. When here also direction is towards the negative direction only. So it is negative going from point O to point R. At point R, velocity would be 0. That is because when the particle goes towards point R, the restoring force, it is towards O only. So it will be decreasing. It becomes 0. The particle crosses point R and goes towards point O, the force is towards the mean position, and also velocity is towards the mean position. Velocity will increase, that is shown by this graph. So this would be corresponding to point R. Similarly, we can show the graph for A also. When the particle is at point A and goes towards point Q, the net force or the acceleration is towards the center point. So this will be the force direction. But force is in this direction, it is negative direction. So when the particle moves from O away towards point Q, then y is increasing. So from this graph, when y increases, A also would increase, but in opposite direction. So even though y is increasing, A also will increase. A will increase, but it is in the opposite direction because the force is towards the mean position. It's like this. The force is towards the negative direction. When the particle goes to point Q, this corresponds to point Q. In that case, A is maximum. When the particle retraces and goes towards point O, then A would decrease, but even now the acceleration is towards the mean position. So A would decrease, but it is still negative only. When the particle comes to point O, A would be 0. When the particle crosses point A and goes towards point R, then the force is towards O now. In this case, the force or acceleration is towards the point O, which is along the positive direction, because of which A would increase. When the particle goes to point Q, A is again point R, A is again maximum. When the particle returns towards point O, still A is towards the mean position. When the particle y is decreasing, A also will decrease. This is the curve for a velocity, time, displacement time, as well as A versus time. Now to understand better way, we can draw the curve backwards. We can draw this also. And you can draw this curve backwards like this. So if you pull this sine curve, this curve by like this, if you pull it by pi by 2, then we get the cosine curve. Let's observe carefully here. That is, when we pull this sine curve in this direction, or think of this curve also, when you pull this curve towards this by pi by 2, we get the displacement curve. That's why the phase difference between velocity and displacement is pi by 2. When you pull this curve, the graph of A, by pi, we get this curve, or when you pull by pi by 2, we get this curve. That's the reason that the phase difference between displacement and velocity is pi by 2. Velocity and acceleration is pi by 2, and displacement and A would be pi.